Okay, so we're into section 9.7. It is far easier than section 9.6. We're factoring some special products. They all follow pattern. I'll try to keep this video short and sweet, just like your little attention spans. Ha ha ha. I used humor to disarm you. What are some extra special patterns I can factor in a jiffy? So let's find out. The first pattern, this is a huge one. It shows up all over the place. You will see this more and more and more in math. It's the difference of two squares. Let's look at the FOIL going forward, because if we're going backward, we should know what's happening going forward. So I have x squared. What happens with my middle two terms? I have minus 4x. I have plus 4x. These cancel, right? Negative 4x plus 4x. They cancel. And then I have my last terms, minus 16. So because the middle two terms cancel, I'm left with what we call a difference of two squares. Difference because of the minus sign, squares because x squared is a perfect square, also 16 is a perfect square. Interesting. So now let's go backwards. If you notice, this falls into the same pattern. I have a perfect square, I have a perfect square. They are subtracting. That means that according to the pattern, what I can do is I can think, okay, how do I multiply to x, x, and x? How do I multiply to 25? Thinking like square root, 5 and 5. Make 1 minus, make 1 plus. The reason this works is because x times x is x squared. Negative 5 times 5 is negative 25. And the middle two terms, negative 5x, and plus 5x cancel. So I'm left with just x squared minus 25. If you are uncomfortable with this pattern, get comfortable with it. Nevertheless, I'll show you this other tricky way of thinking about it. Notice that there's no x term in the middle, so we can think of it as 0x. So if you try to find two numbers that multiply to negative 25 and add to 0x, that will result in negative 5 and 5. So you can do it just like normal, but if you remember the pattern, you can do it in a jiffy. So let's take a look at two examples. Ooh, x squared minus 100. Golly, I recognize a difference of two squares. Here are two perfect squares. Here's a minus sign, so this will factor into x minus 10 times x plus 10. So easy. This one looks tricky. Psych. There are two perfect squares here. Look, 4x squared. This is a perfect square because not only is x squared perfect, also 4 is 2 times 2, a perfect square. I have 9y squared. 9 is a perfect square. Y squared is a perfect square, so that's good. I have a minus sign in the middle. So let's think about the pattern here. How do I multiply to 4x squared? Thinking kind of in terms of square roots. 2x times 2x. Don't choose the 4x and the x. Remember, it's a difference of two squares, so choose the square roots. 2x and 2x. And then how do I multiply to 9y squared? Again, choose the square root, 3y and 3y. If we make 1 plus and 1 minus, then even though this is a super complicated middle term of negative 6xy and positive 6xy, because of the minus and the plus and the fact that I'm using all the same terms here, my middle two terms cancel. So this is the answer. Remember, it follows a pattern. Square root, same, minus, plus. Always difference of two squares. All right, second pattern, perfect square trinomials. Now, let's take a look at this. Noobs, which back in the early days of the internet was the cool way of writing newbies, but I think it has since gone out of style. And leet speak in general is no longer much of a thing due to the prevalence of texting. You all have no idea what I'm talking about. That's okay though. Anyway, noobs will do this. They will distribute the square in and say that this is x squared plus 4. This would result in a situation where Batman would slap you in the face. That's exactly what this meme is saying. Robin's like, hey, don't I just distribute? Batman's like, no, fool. Except he'd be like, no, or something like that, because he's Batman and he uses a Batman voice. Remember what it means to square numbers. It means do this is the thing being squared, do this times itself twice. And now you can see, oh, there's actually a FOIL problem going on here. So I have x squared, I have middle terms, 2x and 2x, that will combine to 4x, so x squared plus 4x, and then my last term is plus 4. If you just distribute, you would get x squared plus 4, and you would leave out this middle term. So don't distribute, turn it into a FOIL problem. It is a perfect square trinomial. Yeah, now you may be thinking, wait a second, we distributed last chapter. Yes, if we had a problem like this, you're allowed to distribute. Notice the difference here. This has addition in the middle. This, just multiplication. So I can distribute exponents when there's multiplication. I cannot distribute when there's addition. Let's work backwards. Now, there is a very specific pattern for these perfect square trinomials. I don't really need you to worry about it. I just need you to think about this. If you have a perfect square on the front, which I do, and a perfect square on the back, try first to guess and check using the square roots. So instead of using 9 and 1, let's start by using 3 and 3. And obviously both of these need to be minus. Does that add up to -6? Well, yeah, it does. And so this is the winning factoring. But remember, since this is a perfect square, instead of writing it as x minus 3 times x minus 3, you should write it as x minus 3 squared to receive full credit. This is fully simplified. Now the special pattern is this. Do you notice how the square root of 9 was 3? 6 is double 3. So that's kind of the special pattern. If you notice that this number in the middle is double the square root of this last number, then it is a perfect square trinomial. But that can be a little confusing, especially when you throw a number on the front here. So let's take a look at 2 more examples. Perfect square. 64 is a perfect square. It's 8 times 8. And I think I noticed that the number in the middle is double 8. It would be 16. 8 plus 8. So yeah, definitely x plus 8 times x plus 8. This is a perfect square trinomial. I should write it as x plus 8 square since there were 2 of them. Now this guy, this is a beast. Thinking about our new methods of factoring like that we did in the last section, I could have 9x times x and 3x times 3x. This, it could be 25 and 1, it could be 5 and 5. So many different combinations. I think that's what I'm trying to say. But since I have perfect squares, let's try them out and see if it works. I should have a minus sign in the middle. So let's do 3x minus 5, 3x minus 5. Now, my outside 2 terms, or my first and last, 3x times 3x, yes, 9x squared. -5 times -5, yes, 25. Obviously, that's why I picked them. Let's check the middle 2 terms. -15x, -15x. Do these add up to -30? Yes, they do. So this is the winning option. Oop, don't leave that as your option though. Write 3x minus 5 squared. Notice that the special pattern here, if I consider this, some of you will get this, most of you won't, that's totally fine. If you consider this to be a squared, then I guess a would be 3x. If you consider this to be b squared, then b would be 5. And if you notice this middle 2 term happens to be 2 times a times b, like a times b is 15x, and then times 2 is -30. But I just feel like that's too complicated to memorize. Just if you see perfect squares on either end, try to do those first. Oftentimes it'll end up being a perfect square trinomial. Not always. Like, yeah, it won't always work out this perfectly, but it did in these cases. All right, summary, difference of 2 squares. This is the pattern that you really need to know. If you recognize 2 perfect squares subtracting each other with no middle term, they factor like this. Take the square roots, put a minus, put a plus. If you see a perfect square trinomial, if you notice this guy and this guy are a perfect square, then just try using their square roots at first and you might get an answer that both binomials are the same. Hey, I kept it to under 10 minutes. Go me!